Hello, my name is Boaz Glassberg. I am a senior studying computer science as a member of Washington State University's Honors College. This video will look at the energy footprint of artificial intelligence, the environmental pressures created by the data centers that fuel AI, and the emerging technologies that are aiming to make AI more sustainable. AI has been developing extremely fast, and the scale of its energy needs is now a growing area of concern for computer scientists and environmentalists alike. The unprecedented growth of artificial intelligence over the last several years has had a massive impact on modern digital infrastructure. The release of systems such as ChatGPT allowed these models to be moved from small-scale research environments into everyday use. Upon its public release in late 2022, ChatGPT reached an astonishing 100 million users in 2 months. This rapid adoption by the public started an industry-wide boom for companies like Google and Microsoft to adopt and develop their own generative AI bots. The expansion that followed over the next few years was driven by advances in large-scale machine learning, a large degree of investment by the industry, and a willingness among major technology companies to integrate AI directly into search engines, software, and consumer interfaces. This early surge had large environmental implications. AI systems are incredibly energy intensive, both while running and during their initial training. As generative AI models were being integrated into more and more applications, their carbon footprints rose dramatically. According to PhD candidate and environmental researcher Alex de Vries, this period marked a rapid expansion and extensive large-scale application, which led to substantial growth in the energy requirements of both AI and inference. Although model training receives more attention in public discussions, inference, where the model generates outputs when given instruction by the user, represents the majority of energy consumption. Google reported that 60% of its AI-related electricity use from 2019 to 2021 came from inference, not training. The training of a generative AI model is a one-time event, while inference continues consuming energy every time a user interacts with the system. As AI becomes embedded in more tools, inference activity increases and the accumulated energy use becomes significant. The energy costs of large models is not small. Training the big science model Bloom required 433 megawatt hours of electricity. ChatGPT-3 required roughly 1,287 megawatt hours, and Google DeepMind's Gopher used about 1,066 megawatt hours. These values show how computationally expensive training these models is before public deployment even. Once in use, the energy demands can increase further. Alex DeVries estimates that OpenAI's infrastructure for ChatGPT requires approximately 564 megawatt hours per day to serve an estimated 195 million requests. That translates to about 2.9 watt hours per query. A standard search query takes about 0.3 watt hours of energy, but according to Google, an interaction with a large language model consumes 10 times the electricity of a standard search. If AI-enhanced search becomes widespread, the energy consumption could rise enough to match the electricity use of an entire nation. Alex de Vries claims it could even match that of Ireland, which consumes about 29.3 terawatt hours annually. If environmental impacts of this growth the environmental impacts of this growth depend heavily on the carbon generation of electricity. If AI is powered by fossil fuels, the emissions caused by AI's spike in power demand would be extreme. Carbon-free energy production varies widely by region, and as Patterson et al. Note in their article, the carbon footprint of machine learning training will plateau then shrink. Choosing low carbon locations can reduce the carbon footprint of powering AI models by factors of 5 to 10. The rapid expansion of AI has placed additional pressure on companies to invest in the availability of renewable energy to facilitate their data centers, and it has brought more attention to discussions about the need for cleaner electricity. To address these pressures, researchers and companies are developing strategies to reduce the energy cost of AI. Patterson et al. Outline four categories of intervention: model, machine, mechanization, and map. Improvements to the architecture of the model can reduce computational requirements significantly. Hardware advances, such as a shift from an earlier generation of GPUs to new systems, have yielded more than a 13-fold reduction in energy use. Advances in cloud computing allow for moving AI workloads into the cloud instead of onto the machine itself, which can improve efficiency as well. Finally, performing expensive computation in areas produced by green energy further reduces the environmental impact. When combined, these measures can reduce carbon emissions for machine learning workloads by hundreds of times over compared to earlier models. New research is being performed to address the rise in expected energy demands through modern environmentally focused infrastructure as well. Engineers Ajagekar and Yu produce propose a variational quantum circuit learning framework to optimize the energy use of data centers using renewable supply. Their model aims to reduce energy use and emissions by up to 12%. Their work shows that new optimization methods can still allow for more efficient use of energy in facilities that power AI workloads. This is important as less wasted energy directly leads to a smaller environmental impact and will help greatly as data centers continue to expand. Environmental researchers Bouaouda and colleagues are performing a complementary strategy to support the rise in solar power. They created models using solar energy forecasting and reinforcement learning to manage the energy use of data centers. Their approach uses hybrid forecasting models to predict the rate at which solar power will generate and then plan accordingly. Because AI inference and training often occur continuously, performing expensive tasks during peak renewable hours, such as during sunlight, um, is one way to curb the environmental impact of these facilities. These methods suggest that sustainable AI development will involve not only improvements to the AI systems themselves, but also where and how electricity is used. This research connects directly to the broader energy use concerns in conservation. The more efficiently data center energy is used, the less pressure there is on existing fossil fuel generation, and the more feasible it becomes to operate large-scale AI systems within the limits of renewable energy production. Reducing the energy footprint of AI does raise concerns about Jevons paradox. This economic principle states that increased efficiency lowers costs, which can then increase overall demand. De Vries highlights this risk, noting that more efficient models may lead companies to integrate AI into more and more unnecessary services, which increases total electricity use rather than decreasing it. This pattern has historical precedent, originating from the spike in coal consumption after the invention of the steam engine in 1800s England. As AI becomes cheaper to run, companies will be more incentivized to create their own AI chatbots, creating growth that offsets the savings from efficiency improvements. For this reason, the environmental implications of large-scale AI cannot be dealt with through improvements in technology alone. Companies must make decisions about when AI is necessary and when it is not. Without restraint, the energy footprint of AI is likely to grow as fast as the efficiency improvements try to reduce it. Despite these challenges, however, there is meaningful progress being made. Technological innovations continue to improve the energy efficiency of AI model performance. Cloud operators are investing in renewable energy, and new technologies are being developed to integrate machine learning with cleaner energy grids. These efforts create realistic opportunities to lower the environmental impact of AI. At the same time, adopting AI responsibly will need restraint because the energy costs are still high. A sustainable future for AI will require a balance between technological advancement and environmental responsibility. The energy demands of AI are significant, but not insurmountable. A combination of improved models, better hardware, renewably powered data centers, and thoughtful use can allow us to use large-scale technological innovations like AI without imposing unnecessary environmental harm. Thank you.